Hello and welcome to my video for 2D vectors where I'm going to talk about tension and pulleys. So in this case here, we want to solve for a couple things. I do have example. It's written as example 3 and 4 because in the last video I did inclined planes. So I'm just going to change that actually. But if you're interested in inclined planes, feel free to take a look at my last video in the playlist. So here it is. Here's the example. Below is an image of a sign at a physics store. If the sign is 25 kilograms, what is the force of the yellow horizontal pull? Okay, so basically what we need to do is we need to think about at this point, what forces are acting on that point. Okay, so at that point, let's draw a free body diagram. We've got that point there. We've got the force of gravity of our sign pulling down. We also have the force of the cable, which in this case, you know what, this question is missing something. Oh, no, it's not. No, it's not. Okay. Assuming that that's the same rope that's holding up the sign. So force of tension, okay? And then we also have another force. That is the force of the horizontal pull. So that force is actually pushing outwards. It's pushing outwards at that point. So I don't really have a word for this force, but I'm just going to call it force. I don't know, force, I'm going to call it force applied for no other reason than I can't think of another name right now. Okay, there might be a better name out there, but those are the three forces that are taking place in this example. Now, the special thing about a force of tension is that a force of tension is actually going to be the same across the entire cable. So keep in mind that this cable is going all the way from here all the way down to here. And since it's not broken up at any point, the force of tension is actually the same all the way through. So this is actually equal to the force of gravity. That's really helpful to know. However, all of our forces are not going in the same plane. So what we need to do is, maybe zoom in a little bit, that's what we need to do. What we need to do is get our horizontal and our vertical components for this force. And so this is 60 degrees up here, based off of the drawing that says 60 degrees. Okay, and so what we need to do is find that this is FG cos 60, and this is FG sine 60 in this direction. Okay, so now what we can do with those understandings or those values is we can say there's an F net vertical, which is MA, and I mean obviously the sign is not moving, so A is 0, so that equals 0, and then we add all the forces together. So FG, actually no, it's not equal to gravity. Hold on a second here. It's going to be equal to a component of gravity. Okay, sorry, I did say some wrong things because it's actually being broken up here in this corner. That's why it's not going to be equal. So sorry about that, guys. I made a mistake. But it will be FT cos 60 and FT sine 60. So the benefit of that is that FG is subtracting from that component in the vertical direction. Okay, which means FG equals that component in the vertical direction. Okay, and let's look at the horizontal direction. So horizontal is that the MA, again, A is 0, so this is equal to 0. So then we can say, well, our force applied minus our force of tension times sine 60, because that's the direction going in the same horizontal direction. So we can flip that around and we can say force applied equals force of tension sine 60. Okay, this is wonderful because now what we can do is we're looking for that force applied. That's the whole point of this question, right? What is the force of the yellow thing? So we need to rearrange to solve for t because we don't know what t is. So let's solve for t in this equation. So what we're going to do is get ft, and we're going to divide by cos 60 on both sides. So fg over cos 60 is ft. So now what we can do is actually substitute that in. So we get f applied equals fg over cos 60 times by sine 60, which we can just kind of put on top. And always fg is mg, so we can rewrite this again, but with mg. So mg sine 60 over cos 60, and that equals our force applied. So let's try it in our calculators. The sine is 25 kilograms times 9.81 times by sine of 60 over cos of 60. And so we get a final answer of 424.7, and unfortunately our sig dig rules tell us we have to have 2 sig digs, so this is no good because now we have to do scientific notation. So 4.2 times 10 to the 2 newtons as our final answer. All right, so yeah, be careful about when it is broken up. Okay, that can really change your answer. And so if you hopefully recognize that if that's fg, if ft was fg, it would actually be falling because it's only a component of fg, so it'd have to be falling. So it doesn't actually work. Okay, so let's continue to look at another example. This is a more pulley example. So up here we have a pulley, up here we have a pulley, and at this point, now you have to think of it as broken up. Just like in our last example, there you have to think about it as broken up. A pulley does not break it up. So a pulley keeps it even across, but a point like this does. Okay, so let's read the question. Neglecting the weight of the strings and the friction on the pulleys, find the mass of box A and B if the whole contraption is at rest. And here are some values also given to us. So we've got this box, which is 1 kilogram, and 2 angles here. Okay, so this is complicated, but we can do this. We can do this. So what we need to do is we need to think about, at this point, what are the forces? And on box B, what are the forces? So first of all, here we've got FGA, so the force of gravity of the box A, and we have the two forces of tension, so FT1 I'm going to call it, and FT2. Okay, those two forces of tension. Now the question is, how much do they each pull? And the answer is, I don't know yet. So what we're going to have to do is look at the other places. So over here we've got the force of gravity on, I'm going to say 1, Fg1, and then also the force of tension. And if everything is at rest, well, guess what? That force of tension 1 is equal to our force of gravity 1, right? Those forces have to be balanced, which is helpful because that tells us this is our force of gravity 1. Okay, so we'll use that in a second, but don't worry, we'll come back to it. Here on box B, we've got the force of gravity B, Ft2, and down here we've got the force of gravity B, which has to be also equal to, because it's at rest, equal to the force of tension, which is helpful because this is also FGB. Okay, this is wonderful, but we're not quite done. What we need to do is break these up into their components. So this is annoying, but it has to be done. And we can also write this as M1G. We can write this as MBG. So again, components over here as well. So the vertical component, let's just talk about the adjacent one first. So we've got MBG times cos 45. And then over here we've got MBG sine 45. And then we've got over here M1G cos 30. And here we've got M1G sine 30. Okay, and looking now at all of the different components and things that are affecting that A position, now let's go ahead and try to solve it by putting in our F net horizontal and our F net vertical. So both have an A of 0. Okay, the question is, what are all the forces? So in the horizontal direction, it's actually relatively easy. We've got M1G cos 30 minus MBG cos 45. In the vertical direction, it's a little bit more complicated. We've got FGA, which I'm going to actually say, hey, this could be MAG. So MAG minus M1G sine 30 minus, in the same direction there, so MBG sine, and let me just move it over, sine 45. Okay, now what we can do is we can take those two parts and solve for the different parts that we need. Okay, so here let's rearrange this. So M1G cos 30 equals MBG cos 45. We're looking for masses of both. Well, in this case, it's pretty easy because the mass B is by itself, and actually there's a G on both sides, so the G's cancel. And so now let's divide by cos 45. So we're going to have MB on this side, and then M1 cos 30 over cos 45 over here. Okay, and for this other one, it's going to be a little bit more complicated. We've got MAG equals M1G sine 30 plus MBG sine 45. So we just added both of these two terms over across the equal sign. Okay, and now we're going to solve for MA. So that's really easy because all we have to do is divide by G, and it cancels everywhere. And so we get M1 sine 30 plus MB sine 45. And because we found MB in the last question, we can also, if we wanted to do it algebraically, we could also do that. So this whole thing, maybe I'll use a different color just to show that really clearly. This whole thing goes here, M1 cos 30 over cos 45. So that's this part, okay? And then times by sine 45, which is what was there before. And so both of them are now in terms of just m1, which was literally just the value of 1. So because m1 was just 1, what we can do is kind of just ignore it and calculate. So we get cos 30 over cos 45 for our first one, and we also get sine 30 plus cos 30 over cos 45 times by sine 45. So our first mass, MB, is 1.2247. Our second one is 1.366. So let's go ahead and just write those down. So 1.2247 and 1.366. So these are both in kilograms. Okay, and I mean, there's not a lot of sig digs here, but I'm just gonna say, hey, it should have been like 1.00 or something like that. If this had more sig digs and this had more sig digs, technically we only have 1 sig dig, but let's do it with 3 sig digs, so just to make it actually a value worth writing down. So here it is for box A and for box B. All right, so here's the pulley example. Here is basically 2 different tension examples and 1 pulley example. I hope this video helps you understand how to solve dynamics questions, but especially 2-dimensional dynamics questions. All right, hopefully this video helps, and good luck.